All right, guys, today we are going to talk about dilations on the coordinate plane. This is the fourth and final type of transformation that we're going to talk about. So you should be on the 6th page of your packet so that you can take notes along with this video. So that page looks just like the page that you see me on right now. It's titled Dilations on the Coordinate Plane. And first, we're going to get down a little bit of key information here about dilations. When we make a dilation on the coordinate plane, we're going to use a scale factor to determine the size and place of our new figure. So a scale factor is a ratio of the corresponding sides in a figure. And the way that we can find that scale factor is by dividing the new by the original. Or you could also think of that as dividing the image by the pre-image. Remember, pre-image is just another word for our original figure. So that's how we're going to find a scale factor if we need to. We can divide like the length of a new side by the length of the original, or we could talk about in terms of coordinate pairs, of ordered pairs. We could divide the original coordinate or the new coordinates by the original coordinates. If your scale factor is bigger than 1, that means you're enlarging the figure in your dilation. So if you have a scale factor of bigger than 1, it's making your image bigger than your pre-image. And if your scale factor is less than 1 or smaller than 1, it will reduce the figure or make the figure smaller than the original was. A dilation, hopefully we kind of remember this, but a dilation is a transformation that either enlarges or reduces the size of an original figure. So enlarge, of course, means to make bigger. Reduce means to make smaller. So a dilation is changing the size of the image. It's not changing the way that it's facing or the orientation of its vertices. It's just changing its size. To dilate a figure, we just multiply by the scale factor. So when we make dilations, we will be multiplying the original lengths or the original coordinates by the scale factor to find our new image. So we're going to start here by dilating and finding what the new dimensions would be if we made a dilation. So here in this first problem, you can see that it tells us we have a scale factor of 2/5, and we have a rectangle that is currently 15 inches by 35 inches. Those are the dimensions of the pre-image. To find the dimensions of the original image, we need to multiply the original dimensions by the scale factor. So to start with, I'm going to multiply 15 times 2/5. So times 2/5. And when I do that, you can use a calculator to do that. That gives us 6. So 15 times 2/5 is 6. That tells us that the side length of our new rectangle is going to be 6 inches. So one of the dimensions is 6. And to find the other dimension, then we're doing that 35 times the scale factor. So you could say 35 times 2/5. And again, if you need to use a calculator for that, that's totally fine. 35 times 2/5 is going to be equal to 14. So our new dimensions of our new figure, if we dilated this original by a scale factor of 2/5, would be 16 by 14 inches. I'm sorry, 6 by 14 inches. Okay, and so you can already see, since we had this scale factor smaller than 1, our dimensions got smaller. So our new figure would be smaller than the original because we had that scale factor less than 1. On this next one, we're really doing the same thing, but you can see we have a scale factor of 3.5, which is bigger than 1, so we can expect our dimensions to get bigger. So we're doing 10 times the scale factor of 3.5, and that is going to give us 35. And then we're doing our other dimension, 22. 22 times 3.5 is 77. So our final dimensions of our new figure here would be 35 by 77 inches. Okay, so hopefully that seems pretty simple. I'm going to leave number 3 for you guys to try on your own. So kind of do the same thing here. If you want to pause the video to do that right now, that's totally fine. When you finish, go ahead and resume the video and we'll move on to the next example. All right, and here in number 4, you can see that we are given ordered pairs instead of dimensions, but really this is the same kind of idea that every new figure is found by multiplying the original by the scale factor. But in this case, we're actually looking for that scale factor. So we're going to see if we can find the scale factor given the new and the original. So remember, up above, one of the first things that we wrote is that we can find the scale factor by doing new divided by original. In this case, that means our ordered pairs. Our new divided by the original. Remember, our new, that would be our image that have these prime marks next to them, and our original are the ones that do not. You really can pick any ordered pair that you want here to find that scale factor. So for example, if I just want to start with D, I could divide my Y values. So I could do negative 16 divided by the original Y value, which was negative 2. Well, we know that negative 16 divided by negative 2 is a positive 8. And if you wanted to check your answer, you could go ahead and you could choose a different one. So for example, you could choose the X value on that D, and you could do 8 divided by 1, which would still give you 8. Or if you wanted to check another pair, you could do that too. For the F's, you have negative 8 and negative 1. Negative 8 divided by negative 1 is also positive 8. So you're going to get the same answer no matter what you do. I will caution you, if there's a 0, like right here, our X values for E were 0, pick a different point because we know we cannot divide by 0. So you have zeros, but just pick a different point to find your scale factor with. And for our algebraic representation here, this is what is happening to get each new X and Y. So just like we did with translations and rotations and reflections, we're just writing this here as an ordered pair. So to get each new X value, really we're multiplying by that scale factor of 8. So each X value is equal to 8 times the original X value. And each Y value is also multiplied by 8. So 8X, 8Y. So here when we write the algebraic representation for a dilation, it's always just going to be X and Y multiplied by whatever the scale factor is. Okay. Here in this next example, again, we're just finding the scale factor that was used to create the dilation. The difference is that in this problem, we are given side lengths instead of ordered pairs, but we're still using that new divided by original to get our scale factor. Here we know that our new figure is this bigger one because it does not have those prime symbols. I'm sorry, that's our original because it does not have the prime symbols, and our new one over here does. So this got smaller, and so you might already be kind of thinking to yourself, well, if the figure got smaller, our scale factor should be less than 1. And to find that scale factor, like I said, new divided by original. So we're just picking a corresponding side. So for example, if I pick XY in my new figure, then I would use that same side, XY, in the original figure. So to find that scale factor, the new length is 12, and the original is 18. So we're doing 12 divided by 18, and 12 divided by 18 can be simplified to 2/3. So our scale factor there is 2/3. And just like we said, since our figure got smaller, we can see that scale factor is less than 1. All right, let's go ahead and flip to the back here. And we're going to do a few examples on the coordinate plane. So it says here, dilate the rectangle shown by a scale factor of 1/3. And this rectangle might be a little bit tricky to see. I'm going to outline it a little bit to make it a little bit more clear. So you can see we've got triangle ABC, D right here. Oops. That one should be a little bit further to the left there. There we go. So it wants us to start here by recording the coordinates of the original or the pre-image in this table. So you can see we have point A to start with, and point A is at -6, 3. We have point B at +6, 3. We have C at +6, -3, and we have D at -6, -3. So if we know that that's our original figure, to get our new figure, we have to multiply each coordinate by that scale factor. So to find the coordinates of our new figure, we are multiplying these original coordinates by the scale factor. So maybe make yourself a note about that on your page, that we're multiplying by the scale factor. So we know that -6 times 1/3 is -2. So if our x value starts at -6, to get our new one, we're multiplying by 1/3. So our new x value would be -2. And our new y value is 3 times 1/3, which is +1. So I could go ahead and I could plot that point. My new A prime is at -2, 1. And so you could even label that here. This is A prime. And we're going to do the same thing to find the rest of the ordered pairs. We're multiplying each coordinate by the scale factor. So B prime is at 2, 1, because 3 times 1/3 is 2, and 3 times 1/3 is 1. So I could plot my point at 2, 1 for B. And I'm going to label that B prime. C prime is at the point 2, -1 after I multiply everything by that scale factor. So I'm going to plot my point here at 2, -1. That is C prime. Pen got away from me a little bit right there. There we go. And the last one is D. So D prime is going to be at the point -2, -1. So like I said before, each of these new coordinates was just found by multiplying the original coordinate by that scale factor of 1/3. So D at -2, -1 is right here. So I can label that D prime. And I could even go ahead now and I could connect my new rectangle. And you can see with that scale factor of 1/3 that our image got much smaller. If we were going to represent this algebraically, we would go ahead and, as an ordered pair, write this 1/3 x, 1/3 y. So each coordinate, the x and the y, are being multiplied by the scale factor of 1/3. It asks us some follow-up questions here below, and the first one is asking us to compare the ratios of corresponding sides. What do you notice? Well, corresponding sides really mean we're comparing side AB to side A prime, B prime. That's corresponding sides. So let's go ahead and let's compare that. If we look at side AB in the original figure, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units long. So I could say, okay, side AB is 12 units long. And if I compare that to its height in the same original triangle, side BC is 1, 2, 3, 4, 5, 6 units long. So AB over BC, that ratio is 2, right? The ratio of the sides in the original figure is kind of a 2-to-1 ratio, that the length is 2 times the width or the height. If I look at the same thing in this new figure, side A prime, B prime is 1, 2, 3, 4 units. So A prime, B prime, we said is 4 units. And side B prime, C prime is 2 units. So again, if I look at that ratio, 4 over 2, well, you can see the ratio stays the same. So you could just kind of note that those ratios stay constant or stay the same. This other question here, it says, did the dilation change or preserve the orientation of the figure and the orientation of the vertices? The orientation of the figure, which direction it's facing, that stays the same, right? AB is still on the top, BC is still on the right, DC is still on the bottom, and AD is still on the left. So the orientation of the figure stays the same. And the orientation of the vertices, they go in order A, B, C, D, and the same for our new figure, A, B, C, D. So here you could say that both the orientation of the figure and of the vertices stay the same. All right, the last thing we're going to do here is we are going to perform one dilation on the coordinate plane. Just one more here. And so number 4 says dilate this triangle here with a scale factor of 2. So again, we're multiplying each ordered pair by the scale factor to get the new point. So here, if A is at the point 3, 3, make sure you're paying attention to the scale here, that this y-axis is going by 3s. Then we're going to multiply that by 2 to get our new image. So here, 3 times 2 is 6, so that x-coordinate becomes 6. And since the y-coordinate of A is also 3, 3 times 2 is 6. So the point 3, 3, the image of that is going to be at 6, 6. So A prime is going to be at 6, 6. B prime, you can see we have at the point 3, 15. So to move that, our x-coordinate is 3. When I multiply that by 2, my new x-coordinate becomes 6. And my new y-coordinate, if we started at 15, 15 times 2 is 30. So I have the new point 6, 30. So I can make a point right here at 630, and this is going to be B prime. And C prime is currently at 5, 3. So if I multiply 5 times 2, my x is 10. When I multiply that y value, 3 times 2 is 6. So my new ordered pair is 10, 6. And I can go ahead and make my point here. This is going to be C prime. So we can connect that to make our triangle. All right, and so then if you wanted, we could also have recorded those coordinates down here at the bottom. So A prime, like we said, was at 6, 6. B prime was at 6, 30. And C prime was at 10, 6. Our algebraic representation, like we said, with dilations, this is pretty easy. We're always just multiplying both the x and the y by the scale factor. So we would have 2x, comma, 2y. All right, I'm going to leave number 5 for you to do here on your own if you want to go ahead and try this last problem. You're looking to dilate this triangle with a scale factor of 1/2. So remember, a scale factor less than 1, you should be expecting this triangle to get smaller. Make sure you record those coordinates, make the dilation on the coordinate plane, and fill in here what that algebraic representation would be. If you have any questions, if there was anything on this video that you did not understand, please send me a message so that I can help you get that figured out while you're working on this last problem.